Hello, everyone. Welcome back to Chem 51 or GOB Chemistry. Today, we're looking at Chapter 13, which is going to be unsaturated hydrocarbons for the most part. We'll look at one example of an aromatic hydrocarbon, just because at this level, there's really one canonical example, but we're not going to be looking at aromatic hydrocarbons in general. Specifically, the content is we'll look at alkenes, which are a cousin of alkanes from chapter 12. We'll look at structures and names of those compounds. We'll then introduce cis-trans isomers and the general process of isomerization. We will look at physical properties and chemical properties of alkenes, and we'll contrast them with similar properties of alkanes from last chapter. Polymers, maybe briefly, just to introduce them. Essentially, the reason why polymers pops in here, a lot of polymer chemistry comes from alkene chemistry, so it's like that aunt that you invite to your Christmas dinner. You just have to invite it, but we're not going to make too much of a deal about it. And then the one example of an aromatic compound. Okay. So without further ado, let's go. All right. Okay, so alkenes. So alkenes differ from alkanes in that they have a double bond. So if you have at least one double carbon-carbon bond, your entire structure is an alkene. Compare that with alkanes, where we only have single bonds. So if you look at the structure on the left, let me make sure I've got my annotation tool clicked. My spotlight. There you go. If you look at the structure here, we can see that carbon still has 4 bonds. It just has a double bond and 2 singles rather than 4 single bonds. We also have a different suffix from our name, so ene rather than ane. So instead of ethane, we have ethylene or ethene. And in general, the structure of an alkene is CnH2n. Compare that with alkanes, which was CnH2n plus 2. Each carbon, if you look at each carbon separately here, it kind of looks like a Mercedes-Benz symbol. We have this 120-degree bond angle. And another big difference with alkenes, double bonds don't twist. So once you form a double bond, it's locked in place, whereas a single bond can rotate. So we have a rigidity about a double bond, and that rigidity will make the structure planar. So it's a 2-dimensional, or at least this example is a 2-dimensional structure rather than a 3-dimensional structure. Okay, let's start naming alkenes. So similar to naming alkanes, we're going to inspect the structure and look for the longest continuous carbon chain that includes the double bond. So if it doesn't include the double bond, it cannot be the longest chain. So in this structure here, we can see that our longest continuous chain includes 3 carbons, because we actually only have 3 carbons in this example. And we have to locate the double bond within that chain. And the convention is to assign the double bonds the lowest possible numbers. So as you can see, it's probably in the next slide. As you can see, the double bond is closer to one end than the, oh, actually, that's a different compound. As you can see, the double bond is closer to one end than the other. So let's get my pen out. Red, hopefully, yes, red. So we can either have carbon 1, carbon 2, and carbon 3, or we can have carbon 1, carbon 2, and carbon 3. So as you can see, the double bond is either carbons 2 and 3, or it's 1 and 2. So we prefer 1 and 2, so because the rule is that you try and minimize the bonds. So actually, this compound is not named on the slide, which is quite random. So we have 3 carbons. We know that that's prop, and it's an alkene, so it's propene rather than propane. But we don't have any, so that's the trunk, if you like, of our tree analogy. We don't have any branches, but we have to locate the double bond. The double bond is between carbons 1 and 2. We only have to name the lowest of those 2 numbers. So we just say it's 1 propene. This implies that we've got 3 carbons, prop. We have a double bond, ene, and the double bond is located between carbons 1 and 2. So it'll be 1 propene. In our next example, let me get rid of my annotations. All right. Again, here we have identified the longest continuous chain, including the double bond, which, as you can see, has 4 carbons in it. So let's number those. And again, we want to give the double bond the lowest possible numbers. So as you can see, the double bond is closest to the left side. So we would number, as you can see here, from left to right, again, to prioritize the double bond with the lowest possible number. So the double bond is between carbons 1 and 2. I only have to name the lowest of those numbers. If I say 1 butene, it's implied that the double bond starts on carbon 1 and stretches to carbon 2. I've got a 4 carbon chain, bute, and it's an alkene, ene. I notice I have a branch, a methyl branch on carbon 3. So I have a suspicion on the next page, we're going to address that branch. Yes, indeed. So we started, oh my goodness, they're dragging it out over many, many slides. Okay. So we've already had this on the previous slide. We have 1 butene. Let's get the slides. So we already had the 1 butene. And now we've got, get my application tool back. We have the 1 butene. And now we notice that we have a methyl group on carbon 3. So we just add 3 methyl. So in total, the name is 3-methyl 1-butene. Okay, so again, if anyone has a question, feel free to interrupt. Otherwise, I'll just keep going. Okay. Let's get my application tool back. Okay. What if we have 2 double bonds? Well, look at the structure on the left. We know that we've seen it with the alkane nomenclature in the previous chapter. For example, when we had 2 methyls, it was dimethyl. So again, we're going to use the prefix di. So a diene is an alkene that has 2 double bonds. Bute tells us we have 4 carbons, so it's a 4-carbon trunk of a tree. It contains 2 double bonds, so butadiene, and those double bonds are located between carbons 1 and 2 and 3 and 4. Again, we only give the lower of the 2. We're always going to have 2 numbers for a double bond. We only have to cite the lower of the 2. In this case, we cite 1 and 3. We don't need to cite 2 and 4. It's assumed that 1 leads to 2 and 3 leads to 4. So we have 1,3-butadiene for that structure. Here we have 6 carbons in the longest continuous chain that includes the double bonds. So it's a hexadiene. It's got 2 double bonds, diene. It's got 6 carbons in its trunk, hexadiene. Those double bonds are between carbons 1 and 2, so we state the number 1, and 4 and 5, so we state the number 4. So we have 1,4-hexadiene. And then on carbon 5, we have a methyl group, so 5-methyl 1,4-hexadiene. Again, like with alkane nomenclature, we separate numbers with commas. we separate words and numbers with hyphens, and we don't have any gaps anywhere in the name. So again, keep in mind that we have to be able to go from the name to the structure, or from the structure back to the name. And the naming convention is designed to be very construction friendly. So it should be really a name as a blueprint to write the structure. So the folks that invented this nomenclature language were very thoughtful. They wanted to help a chemist out. Okay, what if you have a cyclic alkene? Oh, my shirts just fell behind me. So we saw cyclic alkanes or cycloalkanes. Likewise, we can have cycloalkenes. The goal, again, is going to be to give the double bond the lowest possible numbers. We prioritize the double bond. So if we look at this structure here, we have 5. I can get my annotation tool. We have a 5-membered ring, a cyclic alkene. So it's got 5 carbons. It's an alkene, so pentene, and it's in a ring structure, so cyclopentene. By definition, the double bond has to be between carbons 1 and 2. So we don't need to say 1 cyclopentene. It's implied that we're starting counting the double bond between carbons 1 and 2. So then we have to give the branch the lowest possible number. Well, in this case, the number is 1, right? So we state where the branch is, the methyl branch. So we'd have 1 methyl cyclopentene. On this structure, our 6-membered ring is cyclohexene. Again, by definition, we start counting the double bond at carbon 1. So it's going to be between carbons 1 and 2. And then we want to give all the other branches the lowest possible number. So let's look at our options here. So let's say I'm going to ignore these numbers. Let's pretend they weren't there and I didn't know. So I could say, okay, sweet, I'm going to call that carbon 1, that carbon 2, that carbon 3, right? If that were the case, I would have, oh, am I going to be able to write this? I would have cyclohexene. So again, the way I've numbered it now, 1, 2, and 3, I would have 2,3 dimethyl. So it'd be 2, 3 dimethyl. So this is the other possible thing that you might get while you're learning this, right? So you've got 2 options. I've prioritized the double bond between carbons 1 and 2. Option number 1 is either the way it originally was, 1,6-dimethyl cyclohexene. Option 2, the way I've drawn it now, is 2,3-dimethyl cyclohexene. How do we know that 1 and 6 is better than 2 and 3? Simply because your first number is the lowest. The fact that 1 is lower than 2, you're looking for the first instance of superiority. And that 1 immediately trumps the number 2. So that nullifies the entire candidacy of that name. So if ever you're not sure in an exam, for example, try both of your options and then look at the name and go from left to right. Look for the first sign of superiority. And in this case, superiority is the lowest number. That would immediately nullify the second option. Okay, let's do that list here. All right. Okay, so that's enough for naming now. Other than you just need to practice some, that's basically what you'll be practicing. Let's look at a consequence of the rigidity of a double bond. So we don't really look at why a double bond is rigid in this course. You would have to take general chemistry to really get your teeth into that. But what we do look at in this course are the consequences of that rigidity. So it leads to a phenomenon called cis-trans isomers or cis-trans isomerization. So for example, let's take this alkene 2-butene. So it's, let me get my annotation tool. Okay, so it's butene. That tells us we've got 4 carbons. And I've got a double bond in, and the double bond is located between carbons 2 and 3. So we can throw some numbers in here, 1, 2, 3, 4, or you can number it the other way because it's symmetrical about the center. So, but if we try and construct this using a full structure, if we flesh out, actually this would be a condensed structure, sorry. So if we draw out the condensed structures of what this actually looks like, we get 2 options. So we have a CH3. So that's that thing here. We get a CH, which is this thing here. We get the double bond, which is obviously the double bond. Another CH, which is this thing here. And then a CH3, which is that thing here. Okay. Having now done that, I'll get rid of all my scratch work. Okay, so we've got all the bits and pieces, but as you can see, I could have drawn it that way. I've still got all the bits and pieces, and because there is no rotation, they are unique, that they don't rotate into each other. So there is no rotation. I'll put an X through the rotation. So that double bond doesn't twist. So a nice way to do this is, and let me see if I'm actually on camera when I do this. All right, so I'll put my all right. So if you do this with your fingers, that would be the double bond. And my thumbs here would be the structure on the left. So let's say my fingers are the double bond and my thumbs are the CH3 groups. Now, I can't twist my fingers because I'll break them. The structure on the right is if I deliberately break them and now reattach them again, and my thumbs are now up and down, that would be the structure on the right. But clearly, that's different than that, right? So that's a useful thing you can do with your thumbs. So we have to come up with a way to distinguish these 2 structures in the name. So if I say 2-butene, that's vague because there's 2 options. Which do you mean? It's like saying Samantha, and then 2 people look at you. Oh, my name's Samantha. Oh, my name's Samantha too. Which Samantha are you talking about? So we need to add an extra name. So cis means together. So these CH3 groups are together on the same side of the double bond. These 2 CH3 groups are opposite sides of the double bond. So trans means opposite. So this is the trans isomer where the CH3 groups are opposite the double bond. On the left, we have the cis isomer where the CH3 groups are on the same side. So that leads to, let's see if it's probably on the next page. That leads to, yes. Let me get rid of all that chicken scratch from the previous page. So again, it's the same structure. For some reason, the architect of these slides drew it slightly differently. But here's the CH3 group here on the same side as the other CH3 group. And as you can see, why did I do that? I'm sorry, let me get rid of that. Oh, I think it's because I touched the screen, that's why. Okay, I'm not allowed, no. I'm telling the computer to show me a spotlight, and it's not, it's trying to draw on the screen. Let me get rid of that. Let me try and get it back. Okay, I'm just not going to touch the screen. So we have cis-2-butene versus trans-2-butene. So the word 2-butene is not enough. We have to say cis-2-butene and trans-2-butene. So hopefully now you know what that means. Okay. Not all alkenes have cis-trans isomers. You have to qualify. There has to be a qualifying component to your structure. So for example, we've just seen that 2-butene does have cis and trans isomers, but 1-butene does not. And you can see why. If you were to try and draw the opposite structure of this, if you were to break the double bond, illegally twist it, and then reattach it to form this structure, it would actually be identical to the previous structure. So there are no cis-trans isomers of 1-butene. So don't think that every alkene has a cis-trans isomer. You need to have the ability to be a different chemical in the cis-trans form. And the guideline for that is you can't have two identical groups on one of the carbons. Because clearly if you did and you were to rearrange them, they would be the same. So here we have two identical hydrogens, which nullifies any cis-trans isomers. Whereas on the 2-butene that did have the isomers, we can clearly see we have a methyl group and a hydrogen, which are different. And we see that difference in the isomers. Okay, let's look at these three structures here. So we have 1-butene, and then we have cis-2-butene and trans-2-butene. Again, 1-butene has no cis-trans isomers because the two H's are identical. 2-butene has the cis where the methyl groups are together on the same side of the double bond. And the trans isomer where the methyl groups are on opposite sides of the double bond. We've seen in our alkane chapter what the word constitutional isomers are. It's when you remove something and stick it somewhere else, kind of like a Mr. Potato Head toy. So kind of like that. So you are acknowledging that you've broken something and you've reattached it somewhere else. So the relationship between 1-butene and trans-2-butene, they're related as constitutional isomers. How is that? Well, how are they isomers, period? Remember, to qualify as an isomer, before we look at the flavor of isomer, how do we know they're isomers, period? Well, let's look at trans-2-butene. It has 4 carbons, so C4, right? It's got 1, 2, 3, 4. It's got 3 hydrogens, 4 hydrogens, 5 hydrogens, 8 hydrogens, right? So it's C4H8. 1-butene has 1, 2, 3, 4 carbons, C4, and it's got 1, 2, 3, 4, 5, 6, 7, 8. Now my computer's just decided it's going to go sleepy time. Okay, so they're isomers, period, because they have the same formula, C4H8. Okay, and you can see what's happened. If I take 1-butene, I can like cannibalize it by ripping this methyl group off and relocating it over here. So I've Mr. Potato Headed it, I've ripped something off and I've stuck it somewhere else. And therefore it relates as a constitutional isomer. Let's look at, again, if we look at 1-butene and cis-2-butene, again, I can take this methyl group and I can break it and shove it over here, right? If I shoved it over here, I would get them on the same side. You could just flip the whole thing 180 degrees, but you would have the carbons both on the same side of the double bond. So it would morph into cis-2-butene. Okay, this is new. So this will be new for this chapter. What on earth is a stereoisomer? So stereoisomers are related based on shape. Constitutional isomers are, I call them the Mr. Potato. You rip something off, you reattach it somewhere. Stereoisomers are related based on different shapes. So again, we know the isomers period. We know the isomers period because they have the same number of carbons and hydrogens. They have the same number of constituents. But they'd be related as stereoisomers because of this cis-trans relationship. They're unique because they can't twist, but we really don't have to break anything and rearrange it. You know, here I literally had to rip something off and reattach it in a unique location. Here I don't. I just have to change the shape of what I already have. That's the difference, and that's what makes them their relationship stereoisomers rather than constitutional isomers. So that's subtle. I'm sure a lot of people are going to get that wrong, but hopefully they'll reach out to me if they're worried about it. All right, because that's definitely, you know, you can imagine in an assessment, you know, giving us some compounds, which of the following are stereoisomers? Which of the following are constitutional isomers? And then you've got to figure out what's the relationship between those structures. Okay, let's start to look at some physical properties of alkenes. Again, if we go down, we've got ethene, which is 2 carbons, propene, 3 carbons, 1 butene, 4 carbons, 1 pentene, 5 carbons, 1 hexene, 6 carbons, 1 heptene, 7 carbons, etc., etc. If you cast your mind back to this similar diagram for similar table for alkanes, we saw that the only intermolecular force in an alkane is a London dispersion force, and it's proportional to the number of electrons. Likewise here, as you get more and more elements, they come with more and more electrons. So as you go down this column, the number of electrons increases, and so do the physical properties. The boiling point, the melting point. So again, we only have London dispersion forces, and they are proportional to number of electrons. So they correlate with number of elements, yes, but correlation is not causation. They only correlate with elements that are caused by electrons. So some people just say there's more elements. That's just the correlation. It's technically not the right thing. Okay. Okay, so the chemistry of alkenes is a bit more fancy than the chemistry of alkanes because we have a new fancy feature, right? We have this double bond. This double bond is a region of electron density, and it's going to attract things that like electrons. So for example, you can add X and Y to the double bond in what's imaginatively called an addition reaction. Chemists have no sense of humor. So for the most part, so when they come up with names, like they meet in dark castles in Europe somewhere, and they decide, hey guys, hey people, what should we call this reaction where you add something to an alkene? And eventually they stumble upon the answer. Let's call it an addition. And that's about as exciting as these meetings get. So it's an addition reaction because we're literally adding X and Y to the double bond. Notice that we form an alkane-like structure. It really depends what X and Y are. But notice when we add, we lose the double bond. because we have to preserve the 4 bonds around carbon. So if you look at this carbon right now, it's got 4 bonds. It's got 2 singles and 1 double. The same carbon after the addition has 4 bonds. It's now got 4 singles. So a big mistake that you'll see is a student will add the X and the Y, but they'll forget to break the double bond. So if you have something like this, have a look at, if you forget to kill the double bond, you would see that you have 5 bonds around carbon, and that's just not, carbon's not capable of forming 5 bonds. It forms 4 bonds to become isoelectronic with neon. 5 bonds would be isoelectronic with nothing. So remember, after addition, you get rid of the double bond. When we have a double bond, I don't think I've used this vocab with you in the video so far. So there's an extra piece of vocab that we can use to describe this double bond. We can talk about an unsaturated structure. So the presence of 1 or more double bonds makes the structure unsaturated. The presence of only single bonds, we call that saturated. So in addition reaction, we convert an unsaturated alkene into a saturated alkene. So this is one way we can convert one to the other, and eventually we'll see we can go back. We can convert a saturated alkane into an unsaturated alkene as well. Okay, this is a summary of the 4 flavors of addition reactions that we'll worry about in Chem 51. So here we've got a representative alkene. It's a cycloalkene, but that's okay. We can add hydrogen to make, you can see here the H2, we've added these 2 hydrogens here. We call that specific addition reaction hydrogenation, literally because we've added hydrogen. We can add X2 where X is a halogen. So it could be chlorine, bromine, fluorine, or iodine. We add it, or it could be a mixture. It could be Cl2, it could be ClF. So it can either be 2 of the same halogen, or it could be a mixture of 2 halogens. And we call that halogenation because we've added a halogen. We can add H and a halogen, and we call that hydrohalogenation because we've added hydrogen and a halogen. Or we can add water as H and OH, and we just call that hydration. Notice in every case, we've lost the double bond. So again, we've exclusively gone from an unsaturated alkene to a saturated alkane. Okay. When you do that, you can have a variety of products. So here are 2 potential products, and they are constitutional isomers of each other. So let's say we're doing a hydrohalogenation. So we're adding HCl, so that could be a hydrohalogenation. And we've got to decide, okay, does the Cl go on the left and the hydrogen on the right, or does the Cl go on the right and the hydrogen go on the left? Because it matters. If we have the Cl going on the left, in this structure, we would have 2-chloropropane. So I don't need my students to name alkyl halides. But having seen the name right in front of us, we can certainly understand it. So if we inspect what this means, I've got propane, I've got an alkane with 3 carbons. And on carbon 2, I have a chlorine group. So here's my 3 carbons. And it doesn't matter how I label them, either carbon 1, 2, and 3, or carbon 1, 2, and 3. Either way, the middle one is carbon 2, and that's where I've got a chlorine group. So I've got chloropropane on carbon 2, 2-chloropropane. However, if I added the hydrohalogenation in the other way, you can clearly see that the chlorine now is on carbon 1. So what is it? Do I form 2-chloropropane or 1-chloropropane? Well, you won't be surprised to hear that there's a rule. There's a rule called Markovnikov's addition. Which I can find the right place. Probably on the next slide. Yeah. So we're going to follow Markovnikov's rule and do Markovnikov's addition. So briefly stated, Markovnikov's rule will pick one of the products as the only product. This is called the major product or the Markovnikov product. And it essentially says that the carbon with the most H's will get an H preferentially. So if we look at these 2 carbons in the double bond, this carbon has 1 H attached to it. This carbon on the right has 2 H's attached to it. We're not interested in the methyl H's. It has to be directly bonded to the carbon of the double bond. So there's a difference, right? The carbon on the left has 1 hydrogen immediately bonded to it. The carbon on the right has 2 immediately bonded to it. Markovnikov says the carbon with the most H's gets the H. Therefore, the carbon that already has 2 H's will get an additional H. So rather than the H go to the carbon with the least H's, the H goes to the carbon with the most H's. And that's how you can tell the difference between the anti-Markovnikov product. So we would call this the anti-Markovnikov product, which is not formed on this occasion. There are fringe cases where it is, but we don't see them in this course. And our only product is the Markovnikov product. Okay. What if both carbons had the same number of hydrogens? Well, then you would form, then it wouldn't matter because you wouldn't see Markovnikov's rule in action because it would lead to the same, it would lead to an identical product anyway. So Markovnikov's rule is always in effect. You don't always see it if your compound doesn't allow the effect to be seen. So to allow the effect to be seen, your carbons have to have a different number of H's on them. Okay, polymers, it's kind of added as a fringe topic here just because polymers tend to be chain reactions of addition. So if you add, you can essentially connect units of alkenes together to form a long chain. So as you can see in this cartoon here, there we go. Here we've got ethylene, CH2, two carbons with a double bond, that's what I meant. Poly means many, and mer means copy. So a polymer literally is many copies. So we take many copies of this and we can add them together, almost like a daisy chain. And this thing can get really long, and we call that a polymer. So if a monomer is a brick, a polymer is a wall. So we've taken ethylene or ethene bricks and we've made polyethylene or polyethylene, which is a polymer. Most people refer to polymers as plastics. So plastic is the generic name for a polymer. So look around, the room that you're in now, you probably have plastic all around you. The screen that you're looking at this video on is made of plastic. Probably the clothing that you're wearing is made of plastic. The TV remote that you have, because you're not really watching the video, you're just watching the TV, is probably made of plastic. So plastics are ubiquitous in human society. So polymer chemistry is very important, multi-billion-dollar industry, and there are pros and cons to it. So we've all heard about, you can't, for the love of Dalton, you can't find a plastic straw these days because they end up going into the ocean, getting stuck up the nostrils of turtles. So we're trying to avoid plastics, but we still need them. We're just trying to use them a bit more in a more conscientious way. Okay. I'm gonna glance through this. I left these in the slides just for my students to glance through. Polymer chemistry proper, it can be complicated. There's different styles of polymer that you can bump into. I can see some here. Yeah. So once we've added them, this is just more for awareness. It won't be a major part of my course in Chem 51. Some other instructors in general GOB courses might add more emphasis than I might. So you can form these polymers with subtle differences. So for example, here we've got PVC or polyvinyl chloride. So here's the brick vinyl chloride. We have ethene, but instead of a hydrogen on each carbon, one of the hydrogens is replaced with a chlorine. So when they become an unsaturated chain, we get one of the locations being a chlorine, and it's nicely color-coded green here. You can have, if you look at this isotactic version of PVC, you can see that the CLs are all exactly in the same location. Here, the wedge means it's coming towards you. The dash means it's going away from you. All the chlorines are pointing towards you. So that would be an isotactic structure. Iso just means the same. They're all coming at you. Syndiotactic means they vary. So if you look from bottom to top, again, the wedge towards you, the dash away from you. The wedge towards you, the dash away from you. The wedge towards you, the dash away from you. So they are in a regular pattern, but it's alternating up and down, up and down, up and down. So syndiotactic, up and down, regular pattern, but it oscillates. Isotactic, identical pattern, either up, 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 or down, 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 down. Atactic is random. It's a mixture of the two. So if you look here, you've got up, and then you've got up, and then you've got up again, and then up. So you've got 4 ups in a row. You're like, sweet, it's up. And then it's like, oops, now it's down. Okay, is it going to be down 4 times? No, now it's back to up again. So it's an irregular pattern that's not predictable. Here you can see another, so this is polystyrene. So here we've got a benzene ring, this funny hexagon with a circle in it. This is actually the aromatic structure that we're going to see in a few minutes. This is the one example of an aromatic structure that we typically encounter in Chem 51. So we can see if I'll draw the styrene monomer that when we polymerize it becomes polystyrene. So polystyrene is that white packaging, stuff that you get in furniture and what have you. So here's the unit that kind of repeats over and over again. See it again here. And again, I'm just going to keep going. And then here. So instead of the Cl, we would have that hexagon, right? So we'd have two carbons and a hexagon. We lose the double bond, but we retain that aromatic group. So we have polystyrene, symbiotic. Remember, that's the regular oscillation. So we've got right, left, right, left, right, left. Keep going, right, left. We can have atactic polystyrene, which is the unpredictable one. So we have right, left, left, and then right again, and then left. So it's unpredictable. If this kept going, you wouldn't see a pattern emerge. It would just seem random. These different forms of the same thing can add subtle different properties to the polymer. It could make it slightly more dense. It could make it slightly less dense. It could vary the physical and chemical properties of the polymer. So for my students, just awareness of this is more than enough. Okay, so let's move on to that one example of an aromatic compound. So aromatic compounds historically had a pleasant smell. So the origin of the prefix aroma comes from the word aroma. There are many compounds that are not aromatic that have a very pleasant aroma, but historically that was the origin of this name. So I'm trying to get my nice red. There we go. Aroma. These were pleasant smelling compounds. Not all aromatic compounds are pleasant smelling. Ironically, but to be aromatic, you have to obey something called Huckel's rule. We don't follow Huckel's rule in this course because we only look at this member. So how do I know? So this is called a benzene ring. And you can either draw it as a ring with alternating double and single bonds, or as we saw in the previous structure, you can draw it as a ring with a circle. The ring with a circle, to be honest, is the most common way you'll see it. The six-membered ring with a circle. And that's because the double bonds can resonate. So here I've got the double bond on the right, but I could literally migrate those double bonds. So if you're double, you become single. If you're single, you become double. So I'm showing you a counterclockwise rotation. And that would shift the double bond. So instead of having this, I could draw it like this. So to show the fact that you can oscillate those double bonds, we can just draw it like that, where the ring is just an oscillation. If ever you see it like this, it's called the Kekulé structure, Kekulé. So if ever you're asked to write the Kekulé form of benzene, write it with explicit single and double bonds. Otherwise, the circle is fine. This is completely two-dimensional. It's completely flat. All the carbons are in the same plane. All the hydrogens are in the same plane. Importantly, a benzene ring is not an alkene. Even though it has the suffix -ene, benzene is not an alkene. It doesn't have the same chemistry as an alkene. Alkenes don't have aromaticity. Aromatics do. So if this was just a cyclic alkene, we would just call it a cyclic alkene. But it's not. It's got this other emergent property, aromaticity. So again, for us in this class, it's important to know that it is not an alkene. It doesn't behave like an alkene. It behaves like an aromatic compound. Okay, so this is the one single example of an aromatic compound we will see in Chem 51. Okay, I think I've just talked about this on the previous slide, so we'll go over that. It just tells you that you can resonate, and the double bond can be written in the other structure, in the other location. Again, a blend of these two becomes the rings form, and you'll see both. You'll see both in exams, you'll see both in notes, you'll see both online. If you Google benzene ring on YouTube, different people will use both. So just get used to seeing both. Okay, and to finish this off, again, we said that benzene is not an alkene, so it won't undergo addition reactions in the same way that an alkene will. So we know that alkenes, true alkenes, will undergo addition. So here we've got halogenation to form this dibromo substituted alkane. We can't do the same with benzene because it's not an alkene. Okay, so that will conclude this video.